In science and in chemistry, we make observations that can be qualitative or quantitative. And when we make a quantitative observation, there is a physical quantity that has both number and unit. And the number of digits in a number is important to know. When measuring, we record all digits plus one estimated digit. And the tool is going to determine where that estimated digit is. Here I have a decimal. And to the left, I have the ones, tens, hundreds places. To the right of the decimal, I have tenths, hundredths, thousandths. And then each tool would have its own units. This is a graduated cylinder, and we'll measure in units of milliliter. The major division, 1, 2, 3, is in the ones place. And the major division, I would say, looking at the meniscus, I'm looking at this down the center of the tool, at this spot right here. I would say that that's between 2 and 3. And now we look at the minor divisions. Between 2 and 3, there are 10 divisions. This is 2.1, 0.2, 0.3, 0.4, 0.5, 6, 7, 8, 9, 10. This spot is between 2.6 and 2.7. So in the tenths place, we see the minor division. And we are at 6 and a bit more. And now we're going to estimate between the lines for the estimated digit. To the right of the tenths place, the next available place is the hundredths place. The hundredths is going to be our estimated place. And I would estimate that the distance between 2.6 and 2.7 was like 4/10 of the way. I'm going to call this 2.64. So my measurement here is 2.64 milliliters. Measured, estimated. There are 3 digits, 3 sig figs. The tool determines where the estimated digit will be. You'll remember that when measuring with the balance estimates the last digit for us. So it's hard to see, but there's the decimal. And so the value given on the balance is 222.5, and balance is measured in grams. That is the mass being measured. There are 1, 2, 3, 4 sig figs. This value has 4 sig figs. Because the estimated digit is in the tenths place, this balance is called a decigram. Balance. We use these measured values in calculations to answer a question or solve a problem. For example, could this be real gold? It looks like gold. It's shiny and golden colored. Maybe it feels like a metal in your hand. So we need to consider some other aspects to support the idea that this may be real gold, and one of those would be density. Pure gold would be 24 karat and would have a density of 19.3 grams per cubic centimeter. So if we could come up with the mass of the gold, and then because it's an irregularly shaped object, we would find the volume by displacing water. If we have the mass and the volume of the same sample, we could come up with the density. On the left, we have a graduated cylinder, and here we have 10, 20, so there's something in the tens place. And then divisions in between there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have something in the ones place. This is 11, 12, 13, 14, 15, etc. And then the estimated digit will be us reading between the lines. So it looks to me like this is 15, 16, 17, and a little bit more. I'm going to say 17.1. And a graduated cylinder reads in milliliters. This would be my initial volume. And then once the gold, or the chunk of whatever this is put in there, it pushes out the water. And so whatever volume this has is how much water is being pushed. And so I see my meniscus there. To me, it looks like it's not quite to 20. It's 19. It's just a little bit less than 20. So maybe my final volume, once the gold is added, is 19.8 milliliters. So my final volume is water plus gold. My initial volume is just water. And when I subtract, the water subtracts out, and what I'm left with is just a volume of gold. So I put this in my calculator. It reports back 2.7. 2.7 milliliters is my volume of gold. That's how much water was displaced, so that's how much gold there was to displace it. And you'll remember that a milliliter is the same as the volume of a cubic centimeter, which is sometimes called a cc, maybe in medical settings. So because this is a solid, we would probably say that the volume of gold is 2.7 cubic centimeters. The mass given on the balance is 51.842 grams. We put that in our calculator and we get a number. And the number that our calculator spits out is very long. It's equal to 19.20074,074, and the calculator doesn't give us units. Now what I have here is close to the answer, but we're not quite to the answer. We need to consider the sig figs. Here we had 5 sig figs in the mass measurement. We had 3 sig figs in the volume measurements. When we subtracted, we now had 2 sig figs. So we have to consider some rules for handling sig figs and calculations. Let's look at that. So there are 2 rules. One is the adding and subtracting rule. When adding and subtracting, the reported value, which is the answer that you would put in a box and submit for credit, can only go as many places to the right as all the values go. For example, in the lab we make measurements, and one of the things we measure is temperature. And let's say we measured the temperature was 22.5 degrees Celsius. But sometimes in calculations, we need to reflect this same temperature in units of Kelvin. And so the way to get from Celsius to Kelvin is to add 273.15. When we add that on the calculator, we get 295.65. But we don't really know this answer to this place because we don't know what's in the hundredths place for the measured value. The measured value is limited. The measured value is limited to the tenths place. We can only go to the right as far as all values go So even though our calculator reports a 5 here, we can only report our answer to the tenths place. So we look to the right to decide, are we going to round that 6 up to 7 or leave it as 6? There's two schools of thought on this. Some people would say round to even. So if this is an even number and that's a 5, keep the even number. Other people would say, well, it's 5. Anything 5 and more means round up. And they might say 295.7 Kelvin. Both answers are fine. I have no preference about how you round 5s. So when adding and subtracting, we can only go as far right as all the values go. For multiplying and dividing, there's a different rule. When multiplying and dividing, the reported value, what you would report as an answer, can only have as many sig figs as the least precise measurement. Here we have a measurement that goes to 4 sig figs. And then here we have a density, and densities are made of measured numbers. And this density only goes to 2 sig figs. So our answer can only go to 2 sig figs. Okay, so we have a value given, number and units. That's a starting place. And then the question says, how many cubic centimeters? So we're starting with a mass, and we're trying to get to a volume. And the way to go from mass to volume, or from volume to mass, is through density. So I'm going to start with my starting value, 17.44 grams. How do I know to start there? Because I have both the number and units. And then I'm going to use density in a way that the grams cancel, and I end up with cubic centimeters on the top. So we could think of the density as being 9.0 grams for 1 cubic centimeter. And we could flip that number and say cubic centimeters on the top. So now that's multiplying by density, but dividing would be cubic centimeters on the top and 9 grams on the bottom. This isn't density. This is 1 over density, but it is a way that we can use this value of density. So I'm going to put the 9.0 here, and then I plug that into my calculator. 17.44 divided by 9 equals, the calculator spits out a very long number, 1.93 7777778. The grams have canceled. Grams of copper have canceled. And the cubic centimeters of copper are left. But my answer should only have 2 sig figs. So I start on the left and I count 1, 2. I look to the right, that's a 3. That means we don't round up, leave the 9 and 9. The answer is 1.9 cubic centimeters is how much copper we have. Cubic centimeters is a volume, and I'm going to write a subscript Cu to say the volume of copper. Put a box around it, that's our reported value. Okay, so here we're using both of these two rules. We've got the add and subtract rule. Here, we can only go as far right as both numbers go. They both go to the tenths. Our answer goes to the tenths. This has 2 sig figs. And then the measurement sig figs, the multiply divide rule says choose the less precise number, which means the number with fewer sig figs. Our answer can only have 2 sig figs. Start on the left, 1, 2. Look to the right. Does that 9 stay a 9? Yes, it does. And the answer is 19 grams per milliliter. That's our reported value. We've rounded to the correct degree of precision, which is 2 sig figs. We have both the number, which has been rounded, and we have units, and then we put a box around it so it's easy for the grader to find. A happy grader is a generous grader. Make that easy to find. And then we can check it against pure gold. Pure gold has a density of 19.3. We came up with a value of 19. So to 2 sig figs, that's the same value. This may be gold. So remember, there are two kinds of numbers, measured and exact. And so far, I've just been looking at exact numbers. Measured numbers. But there are exact numbers, and exact numbers have no uncertainty. They're known exactly, so they have unlimited sig figs. They're not going to limit the number of sig figs when we add and subtract or multiply and divide. What kind of numbers are exact? Well, counted numbers. I can count small numbers of large, discrete things with no uncertainty. I can count up to 27, and students are discrete. We never have like 27.2 students. And defined would be a ratio that came from a definition. So it might be something like there's 12 inches in a foot per foot. So when I see these units that are, they look derived, they're combined, inches per foot. As soon as I have a per in there, I say to myself, okay, these are both length. Let me see if there's a definition that goes with that. 12 inches equals 1 foot. And if we divided both sides by 1 foot, anything over itself equals 1. When we have an equality, something equal to 1, that makes it defined and exact. I might rewrite this and say 12 inches per foot. So defined comes from a definition. The definition has had some math done on it to come up with maybe a ratio that is equal to 1, and that has unlimited sig figs. So, if you want to know if a number is measured or exact, then you look at the units. Number 1, 14.20 grams. Grams are measured. Number 2, milliliters is a unit of volume. Volume is something we measure. Number 3, seconds are a unit of time. Time is something we measure. 4 degrees Celsius is a measure of temperature, which is something we measure. But students, if it's a small number, we can count. Number 6, inches is a length unit. That's something we measure. Number 7, we have a combination of units, centimeters per meter. And so we look and see if that number makes sense. Does that make sense? Yeah, 100 centimeters equals 1 meter. And anytime we have a relationship using metric prefixes, those are exact. If we divide both sides by meter, we get 100 centimeters per meter equals 1 meter per 1 meter equals 1. And another way of writing 100 centimeters per meter would be to write 100 centimeters per meter. Okay, so we look at the units to decide if it's measured or exact. If it's measured, it has a limited number of sig figs, and we count them. Measured, 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 estimated, 4 sig figs. Measured, measured, estimated, 3 sig figs. Measured, 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 estimated, 4 sig figs. 1, 2, 3, 3 sig figs. But if a number is exact, it has unlimited sig figs and will not limit the number of sig figs in any calculation we do. Here we have a measured number, and we have to decide. We know this is the estimated digit, and that was a measured and measured. Was that measured? No. This 0 is necessary as a placeholder to keep the first measured number in the hundredths place. But placeholders are not measured or estimated, so they're not sig figs. They're not significant. Necessary, but not significant. So we count 1, 2, 3, 3 sig figs. This ratio came from a definition, unlimited sig figs. So we need to talk more about those zeros. Zeros can be necessary, but not significant. Zeros to the left are placeholders. So if we measure something on a balance, and we got a value like this, these zeros are necessary as placeholders. It's necessary to keep the first measured digit in its place. But the first measured digit is this 2, estimated 2 sig figs. Zeros to the left are placeholders. Zeros in between non-zero digits are always significant. If I have a number like this, inches are something we measure, and the estimated place is the last place. So this must be measured, and estimated. This 0, which is in between non-zero digits, was measured. So I count my sig figs, 1, 2, 3, 3 sig figs. Zeros to the right may be significant. What matters is, are they placeholders or are they measured and estimated? So we need to talk about that just a little bit more. Zeros to the right of decimals and digits are significant. If I have a decimal and I have a digit that is, this should say non-zero digits. The 0 to the right is significant. And so that could look like this, 1.0 centimeters. This 0 is to the right of a decimal and a digit. It counts. So decimal, digit, 0, that 0 counts, 2 sig figs. Or maybe it's to the right this way. So this 0 is still to the right of a digit and a decimal. It doesn't matter which one comes first, digits or decimals. The 0 on the right is significant. Placeholder. Here, this is just somebody, we do this by convention to say, oh, watch out, there's a decimal coming. So those 2 zeros, this is just somebody warning you about a decimal coming, and this is a placeholder. Those are not significant. But this one to the right of the digit and decimal, that is significant, 2 sig figs. Placeholders are not significant. So this placeholder is necessary to keep something in its place, but is not a sig fig. Sometimes we can't tell if things are placeholders or measured. Like here I have a number, 1,200 miles, and I don't know, was this measured and estimated, 2 sig figs? Or maybe measured, estimated, and this is the placeholder, 3 sig figs. Or maybe measured, estimated, no placeholders, 4 sig figs. So we would say that when we have a whole number ending in 0, it's a little ambiguous. So whole number means there's not a decimal and some numbers after it. And ending in 0, we have to decide, does that 0 mean something or is it just a placeholder? So scientific notation is the way that we're going to clear that up. All the numbers, all the digits in the number are significant. So there's the number, and now I'm going to multiply it by 1,000. And there's 2 digits, so that's 2 sig figs. If I had meant 3 sig figs, I would have written it this way. And if I had meant 4 sig figs, I would have written it this way. So this is the number. Oops. And this is the power of 10 multiplier. And the digits are contained in the number. So scientific notation always has, to the left of the decimal, a digit between 1 and 9, and then maybe something past the decimal. Let me give you an example of what I mean there. This number is not in scientific notation because to the left of the decimal, I have 2 digits. This number I'm just making up numbers here, is not in scientific notation. It is in exponential notation because we have a number and an exponent. But to be in scientific notation, we have to have a number here that is between and including 1 through 9. Okay, being able to determine sig figs is an important skill. It's something that you will use throughout the semester and in your next class. It is one of those things where if you don't learn it at the beginning, you're going to keep losing a point and a point and a point, and at the end of the semester, you'll be kicking yourself. So if you have questions about sig figs, you definitely need to answer. Thank you for your time.